Okay, now let's talk about conservation of mechanical energy. Um, One of the most fundamental laws in all of physics is the conservation of energy, which states that energy cannot be created nor destroyed. It can only change forms. And this includes all energy. Electrical energy can change to mechanical energy or another electrical energy. Nuclear energy can change forms to like a thermal energy. We can have thermal energy change to a mechanical energy. All these other things. So even mass itself. The Einstein's famous equation E equals mc squared. This is the amount of energy that can be contained in a certain amount of mass, which you'll see this in physics too. But so energy cannot be created nor destroyed; it only changes forms. However, we focus on just mechanics in this course, and so we are going to define conservation of mechanical energy. Now, sometimes I'll say conservation of energy, and what I really mean by this is the conservation of mechanical energy, and this is not always conserved. This is actually only conserved if we have no non-conservative forces present, um, which um, what this means is to have a non-conservative force is that um, the amount of energy an object takes in a path is not independent of the path. Essentially, you can just think that our non-conservative forces, the only non-conservative forces we deal with in this class are friction. Um, so if we have no friction, then we have mechanical energy is conserved. So basically, um, if we have no non-conservative forces, which for our purposes are friction, air drag, etc., um, then mechanical energy is conserved. And so basically, this means that the work done is equal to zero. We have no friction to do work, and so if there's no other forces applied on it whatsoever, so let's say we have no forces acting on it other than gravity or a spring. So no forces other than gravity or a spring, which I'll just say is kx. Then we would have the work done would be equal to zero, which would mean that the change in mechanical energy would be equal to zero, which would mean that the mechanical energy at maybe some first point, 1, is equal to, actually, let's take a step further, some final mechanical energy, ME final minus ME initial is equal to 0. And so then what this says is that the final mechanical energy is equal to the initial mechanical energy. And we may want to look at several different points. And so maybe what we'll say here is the mechanical energy at point 2 is equal to the mechanical energy at point 1. And this is the sum of all the mechanical energies. So elastic potential, gravitational potential, as well as kinetic. So here's a kind of a definition of what we mean by a non-conservative force. And we really need advanced calculus. I think beyond calculus 4 to fully define this. So basically, we'll just say there's no friction. But if the work done on this car is independent of the path, so there's one path here, goes up like this. There's another path like this. If the amount of work done on the car or by the car is the same in both cases, then we say that there are no non-conservative forces and mechanical energy is conserved. But using it is very straightforward. So if there's no friction, then we can say that mechanical energy remains constant. So here's a couple of problems. Try these. We'll do them. We'll kind of do them in class as well. But let's say that maybe we'll do this first one here. Let's say that an object starts out up here. This is point 1 up here. And let's say that the velocity at point 1 is equal to 0. So we have some object that starts out at rest at the top of some ramp, and it's going to go through this loop-to-loop here, and then it's going to go up this curve and so on. And let's say, so if it starts out with some initial velocity equal to 0, then that would mean that its kinetic energy initially is equal to 0 here, right? And if we choose a datum, we'll choose a datum down here kind of cleverly because we see this is as low as it goes. It's really annoying to have negative gravitational potential energy, so it's useful to have your datum be at your lowest point. So your lowest gravitational potential energy will be 0. So if we choose a datum down here, then we can say, well, this is 4 meters up from there, so we can find our potential energy as well. And there are no springs, so this is just gravitational potential energy. And so if this is 4 meters up, the mass is 50 kilograms, then we have the gravitational potential energy is just 50 times 4 times g. So this is 200 g, 200 times 9.8. That would be our potential energy. And the mechanical energy is just the sum of these. So we have our potential plus the mechanical, plus the kinetic is equal to our mechanical. And this adds up to, what is this, 1,960 joules. And of course the velocity, we told you the velocity was equal to 0, so the velocity is 0 here. And then we can go into point 2. Now point 2 is only 3 meters high, so the gravitational potential energy is going to be less, but the total mechanical energy must remain the same. So we can find the difference between the total mechanical energy and the potential energy to find our kinetic, and from there, since kinetic is 1/2 mv squared, we can find our velocity, or really this is the speed. And then same thing at point 3 and point 4. And then actually let's take it a step further. Let's say that we have out here, let's say when it gets back down to our datum where the height is equal to 0, let's say it encounters some friction out here. And let's say that the coefficient of friction, coefficient of kinetic friction, is equal to 0.5. Then we can ask another question. We can say, all right, how far past this, we'll call this 0.5 over here. So how far past 0.5 will it go before friction stops it? And we can use our work energy theorem for this. So what is this distance s? So we'll do this in class, but take a screenshot of it right now and try to work it out before we do it. This one is pretty simple to fill out this table. And if you want a challenge, a little bit more of a challenge after that, try this one here. Think about an object which is up here. So I guess a square is equal to a car on a roller coaster here. There's our key. And let's say that it starts out at the top with an initial velocity equal to 0. And then it goes down through here and up through the loop and back on. Now think back to what we did in chapter 6 with the uniform circular motion. There was a minimum speed right here at the top which this roller coaster must have in order for the people to not fall out. So we have some minimum speed here. So using this minimum speed, go back and find out how high this needs to be if the initial velocity is 0. How high does this need to be in order for the riders not to fall out at the top? And I express this in terms of r. So we have the radius here. And remember that we only had gravitational potential energy up here, but we must have kinetic energy because clearly it has some minimum speed, but it is also going to have some gravitational potential energy up here as well, if we choose this to be our datum. So find out, what does this height need to be, this height h, in order for the cart and the people in the cart to remain in it at the top. It's a fun little problem there. I'll blow it up if you guys want to take a screenshot to solve it. And we'll do this in class as well. But yeah, so conservation of energy is really just the work energy theorem when the work is equal to 0. That's basically what it comes down to. Simplified version of the work energy theorem.